Good. Okay, so we were discussing about bending moment and shear force. Bending moment, shear force, and axial forces on beams. Um, both of you were in the class right now. Luke, were you in the class last time?
Yeah, I was here on Tuesday.
Okay, so then it'll be fine, yes. So I don't think you want me to refresh what we have done. And we are now going to, as I have mentioned, so we learned how to find the internal forces in beams. So first thing is we first need to find out the reaction forces in the same way that we apply equilibrium conditions and find the reaction forces. So we did this last week. It's not last week, Tuesday. Then when they are asking us to find the internal forces, we have to section the beam. So they are asking at a certain point in the previous example that we did. So we had to cut here. So when we cut it, there are actions and reactions. So axial forces are always going like this. Shear forces this direction. So I told you these directions are very important to us, and the bending moments are like this. So they are actions and reactions. So they have the same magnitude, but the opposite direction. So finding these forces and moments is what we call the finding internal forces or analyzing of beams. So we consider the left-hand side of the beam. I told you it is okay to consider either right hand or the left hand, but as a practice, let's always consider the left-hand side. And we apply the equilibrium conditions to this left-hand side, and we consider all the forces in the x direction. So there is only one force N, and it is equals to 0. When you consider all the forces in the y direction, we can say 5 minus v. So 5 is upward, v is downward, so it is equals to 0. So v is equals to 5 kilonewtons. And when we take the moment, I told you, we as a practice, we are always going to take the moment from the left hand side corner, and we write the moment equation. So then we can find the bending moment, which is m, and we find it as positives and negatives. So these numbers with the sign are very important. So this is just for a certain point. And I told you today we are going to learn how to find the shear force, bending moment, and axial forces along the beam, how it is changing along the beam. So we will be able to find it like this. We can do this one. We will draw this one later on. Before that, we'll do simple ones, and then we will do this kind of distributed load ones as well. Okay, now let's see how to do this. So the first thing is, let's take this example. So here they have given us the reaction forces. Now to do this, what we do is first if they haven't given us the reaction forces, we need to find them by applying equilibrium conditions. Then what we do is they're not asking, so we are not going to find for a point C, we are going to find it for along the beam, how it is changing. Now we find out, we start from this left-hand corner and we go along the beam. When there is a load changing the loading system, we draw a line there. So again, I'm moving on and I can see loading conditions are changing. So I can divide the beam into 3 parts. So this is my section 1, section 2, and section 3. So what we did, we start from the left-hand corner and we walked along the beam. And when there is a change in the loading condition, we figure it out, like, we divided it into 3 categories depending on the loading condition. Now we are going to measure x from this end, and you can see when the x is, so there are 3 parts here. So if you consider, if I cut when at x, when the x is between 0 and 1.5, that means I'm cutting somewhere here. So if I cut like that, the section, left-hand side section will look like this. Do you agree with me?
Yep.
And when the x is in the next section, so that means x is somewhere here. When the x is more than 1.5 and less than 4.5, what will happen? If I take the left-hand side of the section, then it will look like this. And again, the next one is at the third side. So that means x is between 4.5 and 6. Then I have another arrangement like this. So I have 11.25 and I have 10 here. And again, I have 15 here and I have N, V, and M. So these are the three possible ways that I can cut. Am I right? Do you agree with me?
Yes.
And these distances doesn't change. So 10 is from the left-hand corner, it is just 1.5 meters away. And this 10 is 1.5 meters away, and this one is 3 meters away between 10 and 15. But what is the section length of this beam section? What is this length? What's that length? That length is x. Am I right? I'm cutting at an x distance. So x can be between 0 and 1.5 if I'm cutting, or x is between 0 and 15, my left-hand side section will look like this. If I am cutting between 1.5 and 4.5, then my section will look like this. And when the x is between 4.5 and 6, the section will look like this. So these are the only three possible sections that we can get. Any question so far? Are you guys okay? Okay, now let's see. So I have it in a nicer way like this. So now we consider one at a time. So let's consider this one and we'll find the unknown reactions and the forces. So if all of these ones have shear force, normal force, and bending moment because they are actions and reactions. So now let's take one at a time. So these are the three sections. Now considering the three sections, let's take the first section and can't we find these numbers? So if I consider all the forces in the x direction, I can say N is equals to 0. And if I take all the forces in the upward or the vertical direction, I can say 11.25 minus V is 0. So V is equals to 11.25. Am I right? If I take the moment now about A, I'm taking the moment about A. I told you to take it always from the left-hand corner. I can say M minus Vx is equals to 0. Why I put Vx? Because this distance is x. Am I right? So I can say M is equals to Vx. We already know 11.25x. So you can see from x is equals to 0 to 1.5, axial force is 0. Shear force is a constant, which is 11.25 kilonewtons. And the bending moment is not a constant, it is changing. It is linearly changing. So our x is changing from 0 to 1.5. So we can say when the x is equals to 0, our bending moment is 0. When the x is equals to 1.5, bending moment is something else. So it is a straight line. It's going like a so it's changing with the x. So we can if we want to, we can draw from this part. So I'm only considering this one here. So if you consider this, if you want to draw we are normally drawing the shear force, axial force, and bending moment diagram underneath the beam. So you can say normal force for the axial force is 0. Shear force, V is what is happening with the V. V is a constant, which is positive 11.25 kilonewtons. If you draw the bending moment, M, you can say when x is equals to 0, the bending moment is 0. When x is equals to 1.5, m is equals to 11.25 times 1.5, which is 11.25 times 1.5, which is 16.875. So this is changing like this. 16.878 and 875 kilonewton meters. So is that hard to draw up to here? Are you guys okay up to here? Any question?
So you've just drawn 3 graphs there.
No, we draw 3 graphs means N, V, and M, you mean?
Yeah.
Yes, yes. So we need to draw the axial force, how the axial force is changing. So this is just from 0 to 1.5 part of the beam. So axial force is 0. So throughout it is 0. And shear force is a constant to 11.25 throughout this distance. It is 11.25 kilonewtons. But bending moment is changing from 0 to 16.875. Linear graph. It's like y is equals to mx type. Yes, so we draw 3 graphs because axial force, shear force, and bending moment.
Yep. Thanks.
Okay. Any other questions? Okay, so I want to see whether you have understood this. So can you do the same thing for the second section? I just want you to find the N, V, and M considering this section 2. Apply the equilibrium conditions and find these 3, V, N, and M. Did you find N? What did you get for N?
It's still 0.
N is 0, that's right. So all 3 of you, do you get N is 0? There is no mainly in beams and axial forces are 0 because all the forces are lateral forces. There are exceptional situations, but in most of our cases, N is 0. How about the V? So these are the vertical forces. You have 3 vertical forces. When you consider the vertical forces, 11.25 upward, 10 is downward, V is downward, so this is equals to 0. So we get V as 1.25 kilonewtons. Do you get the same?
So is that 1.25 down?
1.25 down, yes.
Okay, yep.
So we always put the V down for the left hand side. And if it is positive, then that means it is down. Make sense?
Yep.
Okay. So then how about the moment? If you take the moment about A, how can you write the moment about A? So this is A. So you are taking the moment M is counterclockwise positive. Then you have minus V times X. Am I right? And minus 10 times 1.5 is equals to 0. Is this right? Is this right, guys? Now, if you make them the subject, you can say, this is equals to 15 plus 1.25x. M is equals to 15 plus 1.25x. Is that right? Do you get the same? Or if you don't understand, just tell me, I will redo it. Do you get 15 plus 1.25x?
Yeah, I got it.
Okay, so I assume all three of you got it. Okay, so let's leave it like this for the time being. Okay, so we have M is equals to 1.25x plus 15 or 15 plus 1.25x, and this one is 11.25x. And this is this. We found, and N we found for the section. So can you do the same for the last section? I'll give you a few minutes. So n is still the 0, right?
Yes.
How about v?
Minus 13.75.
Yes, that's right. How about the m? What do you get for m? So if you take moment about A, you have m negative 10 times 1.5, negative 15 times 4.5 minus Vx is equals to 0. Did you write the equation similar to this one? Or if you have any errors, let me know so that we can make sure where we went wrong.
No, I've got that.
How about others?
Yeah, I got that as well.
So if we make them the subject now, so you can when you are substituting now, you need to be very careful. When you are substituting v need to be substituted with the sign, with the negative sign. So this will become a positive. So negative will become positive. So your m, if you make the m the subject, you get this. So do you get the same? So you can see how the m is changing with the x. Do you have the same?
Yep.
Okay, now let's draw this. So now let's draw. So I have summarized everything here. So we are now going to draw this. So here, n, if you look at n, it is whatever the x is, n is 0. So our axial force diagram, we use these abbreviations. Okay, so axial force diagram AFD, shear force diagram SFD, bending moment diagram BMT. So we are drawing it underneath the beam, and we can see it is 0 throughout. I can draw a line like this. But V, if you look at V, what is happening? It's 11.25 here, kilonewtons, and then it is 1.25. Then this one become 1.25 kilonewtons, and then it is a negative 13.75. So that is in the negative side, negative 13.75. So we can say axial force is changing like this. Does that make sense?
Yep.
Okay, now what is happening to the bending moment? So here we can now write it. So when x is changing from 0 to 1.5, so when the x is equals to 0, m is equals to 0. When the x is equals to 1.5, we found m as 16.7875 or something, isn't it? It's kilonewton meters. Is that right? I think it is right. 11.25 times 1.5. Yes, that's right. Now, if you, for the next section, so that we can draw. So it's going like this, and this value is 16.875 kilonewton meters. Then what is happening? Now you have a different equation. So when is x is equals to 1.5, your m is, if you put the number here, your m you can calculate, just put 1.25 times 1.5 plus 15. So if you put these numbers in the calculator, I think you get 16.875. So it is starting from here. Is that right? Is it right? Do we get 16.875? When x is equals to 4.5, what is happening? So m is equals to 1.25 times 4.5 plus 15. So when you put this in the calculator now, when x is equals to 4.5, so 1.25 times 4.5 plus 15. So that is 20.625. Do you get the same? So it is going like this. So I think I have, I'll make this one a little bit lower so that can go. It's not the same slope, okay? There are two different lines. They have different slopes. Not the gradient is not the same. So like this. Okay. So this one is 20.625. Similarly, last one, can you tell me the starting point and the ending point? Can you tell me the starting and the ending? Just use the third equation, this equation, and put the boundary condition. So 4.5, when x is equals to 4.5, what is m? When x is equals to 6, what is your m? Can you find me and tell me? So for the last part, were you able to find the starting and the ending? When x is equals to 4.5, what is m?
Uh, 20.625.
Yes. When x is equals to 6,
I got 0.
yes. So it's going
Yeah,
like,
0 to.
are we good?
Yep.
So we call the shear force, axial force, and bending moment diagram. So you have to remember a few things here. You need to name which one is what. So when I see, I should be able to, in your exam, I should be able to identify which one is what. So you need to write the name, AFD, SFD, or bending moment diagram, and you need to put the numbers on the graph with the units, with the signs. You need to put them in on the graph. So that's all. So it's not a big thing, but most students are going wrong with this because they are not doing it with the steps. If you avoid step or if you go with shortcuts, then it's easy to go wrong. Okay, so we'll do one more. I want you to do this one. I'll give you the support reactions. So these are the two support reactions. I will give you a few minutes for you to try. So first, can you tell me how many sections you have to do? If you go along the beam, where are the loading conditions changing? Don't get all this all the time. So the loading conditions are changing here. Do you agree with me?
Yep.
So you need to consider when x is between 0 and 3 and also when x is between 3 and 6. Okay, I'll give you a few minutes. Please draw this one. I'm going to end the slideshow and I'm going to put some more pictures. So can you draw this diagram and work on it till I put few other beams. Okay, so you should have drawn it like this. Is that what you have done with the actions and the reaction? Do you have two sections like this? Now find V, N, and M for both. Separate. If you finish one section, let me know. I want to see what you got. So for the first section, what did you get for N? N is normally 0, that is 0. So V is what? Did you get V as negative 5 kilonewtons?
Yes.
Okay, that's good. Anyone got anything else?
No, I got the same.
Okay, now take the moment about A. So we have M minus Vx is equals to 0. So M is equals to Vx, which is negative 5x. Do you get the same for N?
Yeah, I got that.
Good. Now the next part. So the next part, N is 0, V is negative 5 kilonewtons. Do you get the same? You get negative 5, it's same, isn't it? Couple moment is a moment. It's not coming to your force equations. It's a moment. 30 is a moment, couple moment. So it's not, it doesn't have, like, there is no net force. Now, if you take the moment about A, so you have you have M, minus 30, am I right? Minus Vx is equals to 0. Is this your moment equation? Do you get that? This 30 is a negative, clockwise couple moment. So it's negative 30. About A, we are taking about A. So this one is going this way, this one is going this way, that one is going that way. You get the same?
Yes.
Okay. So if you make the M the subject now, M is equals to 30 minus 5x. Is that right?
Yep.
Okay, now let's draw this. Now this is N is 0, V is negative 5, M is negative 5x. Okay, let's put the boundary conditions now. So let's draw this part. So N is 0, so up to here halfway, N is 0. And this one is negative 5, so I can write it as negative 5 kilonewtons. And this one, now we have two boundary conditions. When x is equals to 0, M is equals to 0. When x is equals to 3 meters, M is equals to negative 50 kilonewton meters. Is that right?
Yep.
So that will be something like this. So this is negative 15 kilonewton meters. Okay, now the next section. So these two doesn't change. So I can extend this to, this is not changing, it's the same. But what is happening to the M? If you put the boundary conditions now, can you tell me when x is equals to 3, what is your M? And when x is equals to 6, what is your M? Can you tell me? When x is equals to 3, M is what?
Minus 15.
Are you sure? So we are looking at this second M equation. M is equals to negative 5x plus 30. When you put 3 for x, you get negative 15 plus 30.
I was positive 15.
It is positive 50. And when x is equals to 6, M is 0. So that will be going like this. So this is 15 kilonewton meters. So you can see this distance. So you have 30 here. See, negative 15 to positive 15 is 30. That is this couple moment. So you can see that couple moment in the bending moment diagram. That difference is your couple moment. Is that clear?
Yep.
So that will be look like this. So any question, you will get something like this in your mid-quart exam. Different beam, but you do the same procedure. You take the same steps. And also you have a trust question, and you have a beam question, and also you have a question with force, what we call it, simplification of force couple systems. I will do some questions before your exam. So you definitely this will be in your mid quarter. Do we have any question? Okay, so I want you to try this one. You think about how many sections you need and then section it. So this is our third one. So if you do this one, I think you are okay. Third example. How many sections you need to do?
3.
So you need to cut like this. So 1, 2, 3, that's right. So these are your sections. So the first section, I hope you have finished. N is 0, V is 0, and M is -30. If you didn't get this, tell me, I will write the equations. Do you get this?
Yes.
Yep, I got that.
Okay, that's good. Next one, N is 0. If you write the V is 5 kilonewtons. If you write the M, you can write M as, I'm going to write the equation because you have many things in it. So taking the moment about this end, left-hand end, so you have M plus 30 and plus 5 times 1.5 minus Vx is equals to 0. Do you have the same equation? We can make the M the subject now. So M, if you make the M subject, so we have -30, -5 times 1.5. So 5 times 1.5 is 7.5 plus Vx. So we can say -37.5 plus Vx. So we can say -37.5 plus 5x. So this is my M. Do you get the same, or have I done anything wrong? So this is not 1 point all the time. This length, don't forget it. The length, the section part, total length is x all the time. It is x. So these are x's. This is x, and this is x, and this is x. Now, if you put the boundary conditions to this one, your x is equals to 1.5 and x is equals to 4. Those are the boundary conditions, and you can find them. This is what I got. What do you get? So you can do the same for the last section. I'll give 2 more minutes.
I think I've done the last one.
Okay, let's see. So N is, how about others? N is 0, V is negative, V is, positive 10. Have you all finished? M plus 30 plus 5 times 1.5 plus 5 times 4.5 minus Vx is equals to 0. So you can now say, I'm going to add all this together because they all are positives on this side. So I'm going to add all this together and see. 30 plus 5 times 1.5 plus 5 times 4.5. That is 60. So we can say M plus 60 minus Vx is equals to 0. So we can say M is equals to V is 10, 10x minus 60. So this is what we get. Is this right?
Yeah, that's what I got.
Okay, now let's put the boundary conditions. X is equals to 4 point. If anyone got something else, let me know. Okay, I'll explain again. If it is, so this is 6. Total length is 6. 6. M. So this one, I think we get negative 15 kilonewton meters. This is 0. Any question?
Nope.
Are you all okay? All 3 of you are okay?
Yep, I'm all right.
So I assume all are okay. So let's draw this one now. So we need to remember N is 0, V is changing. So let's do. So when we draw, we are drawing underneath this, So we can draw like this. So I'm not going to draw the shear force diagram because axial force diagram, it is 0. So let's draw the other two. So here, V is 0, 5 and 10. So V is 0, then 5 and then 10. So it's going like this. So this is my shear force diagram. This is 5 kilonewton and this is 10 kilonewton. And the bending moment is a constant here, negative 30 kilonewton meters. Then it is changing from negative 30 to negative 15. So it's going like this. So this is negative 15 kilonewton meters, and then it is going to 0. It's from so these are our diagrams. Do you guys are okay? Do you have any question? Are you okay with this?
No, that looks good.
Okay, so I think that's all. Okay. The other thing that I want to tell you is bending moment. When the bending moment is negative, means Here, your bending moment is negative. All the time it is negative. Negative means your beam is bending like hogging. We call it hogging. It's going like this. So it's going this way. So this, if when it is bending like this, it doesn't change the positions in this at the supports. So this unhappy phase is negative. So we call this hogging. Hogging is negative. Happy phase, if it is bending like this, it is positive. That we call the sagging. So in some situations, if you look at in our this one, this side is hogging and this side is sagging. So you can see, you can imagine how it is happening. So hogging one side and the other side is sagging. So if you look at the previous one that we did, this one. This whole thing is sagging. So you can see positive, that means sagging. So your beam is going like this. So happy phase, see, that is why it is positive. So in some question they ask, which part is undergoing sagging? Which part is undergoing hogging? So you need to know how to identify that. So positive, if the bending moment is positive, it is sagging. If the bending moment is negative, that is hogging. That's all I have in this one. Okay. Let me check whether I have more questions. Would you like to try this? This is the hardest that we can give you. I told you, you only have uniformly distributed loads, and actually in the universities, those students, they have other different types of distributed loads as well. But in our case, this is more than enough. So if you get a question like this, let's see how to do this. And so here again, you need to section at two places, two sections. When you do two sections here now, okay. Sorry, I need two parts. So one part will be like this. And the other part will be like this. Okay. Before I do, I would like you to try this, please. Think a little bit. This is the hardest that you can do. So I hope you understand why I divided it in two sections. So here you have a distributed load. Apart from that, you have a point load as well. Okay, so you have both here. In this point, your distributed load is changing, and also there is additional point load. So that doesn't matter. You still have two sections. That's right. That two sections. So I have drawn that. So here we have N, B, and N. Here we have N, B, and N. Now your yeah. So think and do. I will help you later on. Like after you try by yourself. Okay, so when you have a distributed load, what I told you to do for, not for the bending moment, but before, whenever we have distributed load uniformly or triangularly, what we can do, we can simplify it to a single force. Am I right? If I simplify this to a single force, if I make this to a single force, can you tell me what is the magnitude of the single force?
1 Newton there. Kilonewton.
What is this?
Sorry, 1 kilonewton. That's 2 meters.
No, I sectioned it at x distance. Didn't I? Didn't we cut by x distance all the time? This is x, isn't it? All the time we cut at an x distance. So I didn't cut at 1 meter. I'm cutting at x distance. X can be from 0 to 2 meters. Am I right?
So it's x over 2 then.
Yes. So this will be x over 2. Do you all agree with that? Do you agree with that? So where it is acting at which point?
Also the x over 2, wouldn't it?
Yes, so halfway. Halfway means this is x over 2. And how this x over 2 came? Because this is 0.5 times x. So 1 meter within a meter, 0.5. Within x, it is 0.5 times x. So that's how this x over 2 came for the magnitude. And the distance is always halfway for uniformly distributed load. So we have found that. So instead of having this distributed load, you can just have one force, which is x over 2 kilonewtons acting at x over 2 distance. Now you do the same thing. There is nothing different. You do the same thing. So how do you find the V? N is 0, don't worry about them, okay? How do you find the V? If you consider all the forces in the upward direction, you have 1.5 minus x over 2 minus V is equals to 0. Am I right? Then you have V is equals to 1 over 5 minus x over 2. The difference is here, your V also a function of x. Agree?
Yeah.
Okay, so you can put the boundary conditions from 0 to 2 and you can find V. Later on, we'll do that. Now write the M. So if you take the moment about the left-hand corner, this point. So you have M minus Vx minus x over 2 times x over 2 is equals to 0. Do you agree with that? Is that right? Is it right, guys? If you don't understand, tell me. I will show how I wrote it. So you have V times x, this one, and also you have x over 2 times x over 2. So, and also you have m in the counterclockwise direction. It is positive. So you can now write m as Vx plus x squared over 4 And B, you can write 1.5 minus x over 2 times x plus x squared over 4. So you can see you have a quadratic equation. So it is not a linear graph. It is like it's a quadratic graph. It's a curve. You can extend this and you can find m as something times x squared plus something times x plus something. So it's a quadratic equation. You get something like that. So are you okay with getting this one? Moment equation.
Yep.
Okay, so can you write the same thing for the next one? Now you don't need to worry. Now you can just put it as at 1 meter. So this is 1 meter because you have this part totally included in the section. This and also you have 1.5 separately, and you have this one as a 1 kilonewton load acting at 1 meter, isn't it? And apart from that, you have axial force, shear force, and the bending. Now you can write n is 0. I'm not going to write it. So if you consider all the forces upward direction, you have up 1.5 up, -1, -1.5, negative v is equals to 0. So v is equals to -1 kilonewtons. Is that right? Second section is easy. And if you consider the moment, so you have m minus vx minus 1.5 times 2 minus 1 times 1. Then you have, yes, that's all, is equals to 0. So you can write m as 4 minus x. Is that right? So the second part is not a quadratic equation. Only the first part is a quadratic equation. So here you can see when x is equals to 0, your v is equals to 1.5. And when x is equals to 2 meters, your v is equals to 0.5. 0.5. Are you okay with this? So if I show you, let me show you what we had in the other one, this one. So you can see here. This -1 we got. And x, if you can remember this one, see? When x is equals to 0, m is 4. When x is equals to, sorry, when x is equals to 0, m is sorry, x is not, yeah, we can't say 0. X is equals to 2 and x is equals to 4. So when x is equals to 4, m is 0. When x is equals to 2, m is 2. So see this one. So it is changing from 2 to 0. Other part, see, we got 1.5 to 0.5. So you can see that here, 1.5 to 0.5. And if you put this one is -1 throughout. So this is -1 throughout, see? And this is a quadratic equation. If you solve this, you get something times x squared plus something times x plus something. That means it's a quadratic equation. Have you done the plotting of quadratic equations in maths? Have you done that in your maths? Graphs?
Oh, a while ago.
Okay, no, it's okay. I'm not going to give you this kind of a question. So, but I wanted to show you that you have the knowledge to do even this kind of questions now. So you should be fine. But you will get a question something like this, not with a distributed load, just by single loads like this. So drawing bending moment and shear force diagrams. Yeah, so with that, I think you are okay to do any kind of question for beams now. There can be other questions in the the workbook. I took few questions from there, and I think if there are more, or else if you see any beam problem anywhere, you can in a book or anywhere, you can try them. We'll do a few more questions when you come to the intensive session. Okay, so regarding the intensive session, I think we have a big class, about maybe nearly 20. So we have all 3 days in Nirimba. Before I was thinking to have 2 classes in Kingswood, because Kingswood we have nicer rooms, big. It's the engineering faculty in the Western Sydney University, but some of you said that you prefer to do it in Nirimba, so we have all 3 days in Nirimba. You need to print the document, the lab notes, but I will print few so that in case if someone is missing out of that, I can give you that. So you are going to do all the questions, and you will be able to finish your lab reports in the class. You don't have to go back home and do it. So you can finish everything at the end of the class. What else? Yes, so that's it. Do you guys have any question? You don't need lab coats for the fundamentals of mechanics. We are not using any chemicals or anything, but you need to have closed shoes, because there are some weights that you are working on. I will make an announcement anyway.
So are we only doing pracs for the first day?
Yes, we only do practice. There are I think 5 practicals. 5 or
Yeah.
6, yes. So when you do the practicals and when you fill the report, it will take whole day, 6 hours.
Yeah. I don't have any more questions.
Okay. How about Luke and Phil?
Hey, no, I didn't have any questions.
Luke said that you don't have any questions, so Lakshman, I think he left already. Okay, in that case, we'll wind up the class, and I'll see you next week.
Yeah, I'll see you on
Nirimba.
Yeah,
Yeah.
Wednesday, isn't it?
Wednesday.
Wednesdays.
Thank you.
Okay.
Good night.
Good night.